What do the most complex laws of quantum physics have in common with an ordinary kettle boiling on your kitchen stove? At first glance, absolutely nothing. We've grown accustomed to thinking of nuclear power as something straight out of science fiction. Mysterious equations, reactors hidden beneath thick layers of concrete, and technologies understood only by a small circle of nuclear scientists. But the reality is far more ironic and surprising. The truth is that a nuclear power plant is, in essence, the most expensive, ambitious, and incredibly complex steam engine in human history. The pinnacle of engineering, a colossal project costing billions of dollars, exists for one single fundamental purpose: simply to boil water. The only difference is where the heat comes from. To generate electricity, humanity has grown accustomed to burning something: coal, gas, or fuel oil. But a nuclear power plant doesn't burn anything. It extracts an incredible amount of heat from a process invisible to the naked eye: the fission of a heavy atom. A single tiny nucleus, as it breaks apart, releases enough energy to spin giant multi-metric ton turbines and light up entire metropolises. A fuel pellet the size of your fingertip contains as much energy as a metric ton of high-quality coal. Today, we'll take this technological marvel apart, piece by piece. We'll follow the entire journey, from the invisible nuclear collision deep underwater to the electrical current in your outlet. You'll learn how engineers manage to keep a physical reaction capable of melting steel under tight control, how water prevents the system from overheating, and why the massive concrete towers, from which thick plumes billow, are actually factories for producing ordinary clouds. We'll dive into the mechanics of one of the most sophisticated energy systems on the planet. No myths or scare stories, just pure physics and engineering genius. It all begins in the most secure part of the power plant, inside the reactor core. Hidden beneath a massive steel lid and thick layers of dense concrete, this space is filled with completely clear water. This is where the fuel is loaded. But it looks nothing like fuel as we usually think of it. No black mountains of coal or endless gas pipes. Reactor fuel consists of tiny, perfectly smooth ceramic pellets. They are carefully stacked on top of one another and placed inside long metal tubes made of a zirconium alloy, which are then assembled into massive fuel assemblies. The metal inside these tubes holds a fundamental secret of nature that physicists unraveled less than a century ago. It concerns a specific isotope, uranium-235. The fact is, uranium doesn't burn, it doesn't need oxygen to release heat, and it doesn't leave behind the usual ash. Instead of chemical combustion, it does something much more elegant and grand. It splits its own nucleus. To understand the mechanics of this process, imagine a classic pool table. The heavy, particle-packed nucleus of uranium-235 is like a tightly packed pyramid of balls right in the center of the table. Now imagine that another solitary ball, a free neutron, crashes into this pyramid. From the impact, the nucleus becomes critically unstable and literally splits into two parts. It is in this fleeting instant that the greatest miracle of nuclear energy occurs. When the nucleus splits, a colossal amount of kinetic energy is released. The resulting fragments fly off at incredible speeds, collide with neighboring atoms in the lattice, and cause them to vibrate wildly. In the language of the macroscopic world, this subatomic vibration means only one thing: extreme, intense heating. This is precisely the heat we need to turn water into steam. But the most interesting part happens next. When a uranium nucleus splits, 2 or 3 more free neutrons are ejected from it. They fly on and strike neighboring uranium nuclei with the same precision. Those nuclei also split, releasing another burst of heat and emitting 6 more neutrons. Then the number grows to 12, 24, 48. This is called a nuclear chain reaction. The process of neutron multiplication grows exponentially in a matter of millionths of a second. Inside the metal tubes, right beneath the water's surface, a subatomic storm of incredible density rages. And this is where the most intriguing engineering question arises. If this reaction accelerates at such a staggering rate, why doesn't the reactor melt down within the very first seconds of operation? How did engineers manage to rein in this invisible chaos and make it run like clockwork, smoothly, predictably, and absolutely safely for decades? The answer lies in precision, physical control. To tame the nuclear storm, engineers use sophisticated physics. Inside the reactor, control rods made of boron or cadmium are positioned between the fuel assemblies. These act as the system's brakes. They absorb neutrons, allowing operators to smoothly regulate the reactor's power output. But the main secret to safety is water. It doesn't just cool the reactor, it slows down fast neutrons, making the chain reaction possible. At the same time, the water itself acts as a safety mechanism. If it turns into steam, the reaction dies down, since steam cannot effectively slow down neutrons. This is a built-in natural safeguard. The water from the reactor, heated to 300 degrees, is radioactive, so it is contained within the primary circuit. It transfers heat to the secondary circuit via a steam generator. There, pure water is converted into high-pressure steam, which roars toward the turbine. This is a shaft the size of an airplane fuselage, studded with thousands of blades. Spinning at tremendous speed, the turbine drives an electric generator. Inside it, a powerful magnet rotates around copper windings. Thus, according to Faraday's law, the mechanical energy of the steam is converted into an electric current that flows into your outlets. After passing through the turbine, the steam must be cooled so it can re-enter the cycle. This is where cooling towers appear on the horizon, those very same gigantic structures that many mistakenly take for smokestacks belching toxic fumes. Let's debunk the myth. No combustion takes place there. They are giant coolers. The spent steam is cooled by river water and then sprayed inside the cooling tower. A counterflow of air cools the water, releasing only pure water vapor into the sky. This is not a pollution factory, but in fact the largest and most environmentally friendly cloud factory on Earth. Thus, step by step, the untamed energy of the atom is transformed into a stable flow of energy that ensures our comfort while remaining a model of engineering excellence. After the steam strikes the turbine blades with tremendous force, does its job, and causes the shaft to rotate, its energy is exhausted. It can no longer drive the massive machinery, but it cannot simply be released into the atmosphere or left in the system. It must be converted back into water so it can be sent back to the steam generator. This cycle must be endless, and this is exactly where they appear on the horizon. Giant concrete towers with wide bases, which many mistakenly call the stacks of a nuclear power plant. You've probably seen them in movies, and they're almost always shrouded in an aura of ominous, toxic smoke. Let's debunk this myth once and for all. No smoke ever comes out of these towers. There's nothing to burn. Inside the cooling towers, there are no chemical reactions, no CO2 emissions, and no combustion byproducts. What you see rising into the sky is ordinary water vapor, the very same steam you see rising from a mug of hot tea on a frosty day. A cooling tower is simply a giant cooler. The spent steam enters a condenser, where it is cooled by cold water drawn from a river or pond. This water absorbs heat from the steam, heats up itself, is pumped to the top of the cooling tower, and is sprayed inside. As it falls, a counterflow of air cools it, transforming the heat into those very snow-white clouds that drift away into the sky. This is perhaps the most eco-friendly cloud factory ever built by humans. We've traced the atom's journey, from the invisible fission deep within the reactor, through the power of compressed steam, to the roar of the turbines and the gentle steam rising into the clouds. A nuclear power plant is neither magic nor a futuristic fairy tale. It is a triumph of engineering ingenuity. It's a way to harness the microscopic energy inherent in the very structure of matter and harness it so that it works reliably for our comfort 24 hours a day, 365 days a year. As you watch this video, thousands of metric tons of uranium are quietly fissioning, powering generators across the planet so that you can simply flip a switch. If you enjoyed this in-depth look at how our reality actually works, subscribe to the channel. It's only going to get more interesting from here. We'll continue to dissect the technologies that drive our world, but which are usually shrouded in mystery. Click the bell icon so you don't miss the next episode. And remember, behind every everyday object lies far more amazing physics. See you next time.